Welcome to the world of Bayesian learning, a cornerstone of modern machine learning. Bayesian reasoning offers a probabilistic approach to inference, allowing us to make optimal decisions by considering both observed data and underlying probability distributions. This method is not just a theoretical tool, it's widely used in practical applications from spam filtering to medical diagnosis. In this video, we'll explore why Bayesian learning is so important, how it works, and what makes it unique compared to other learning algorithms. Let's begin our journey into the logic and power of Bayesian learning methods. Bayesian learning methods are essential for two main reasons. First, algorithms like the naive Bayes classifier use explicit probabilities to solve real-world problems efficiently. Second, even algorithms that don't directly use probabilities can be better understood through the Bayesian lens. This perspective helps us see the underlying assumptions and strengths of various machine learning approaches. By incrementally updating the probability of a hypothesis with each new example, Bayesian methods offer flexibility and robustness, making them invaluable in uncertain or evolving environments. Sets Bayesian learning apart. Each training example can increase or decrease our confidence in a hypothesis, rather than eliminating it outright. Prior knowledge is combined with observed data, allowing for more informed decisions. Bayesian methods can handle probabilistic predictions and classify new instances by weighing multiple hypotheses. Even when computations become complex, Bayesian approaches provide a gold standard for optimal decision-making, serving as a benchmark for other methods. Despite their strengths, Bayesian methods face practical challenges. One major issue is the need for initial knowledge of many probabilities, which are often estimated from background knowledge or assumptions. Another challenge is the computational cost of determining the optimal hypothesis, especially in complex scenarios. However, in specialized cases, these costs can be reduced, making Bayesian methods more accessible for real-world application. The heart of Bayesian learning is Bayes' theorem. This fundamental formula allows us to update our belief in a hypothesis based on new evidence. By combining prior probability, the likelihood of observed data, and the overall probability of the data, Bayes' theorem calculates the posterior probability, our updated confidence after seeing the data. This process is the backbone of Bayesian inference and underpins many machine learning algorithms. Bayesian learning, we often seek the most probable hypothesis given the data. This is known as the maximum a posteriori map hypothesis. Sometimes we assume all hypotheses are equally likely before seeing the data, leading us to the maximum likelihood ML hypothesis, which focuses solely on the likelihood of the observed data. Both approaches are crucial for different learning scenarios and help us make informed predictions. See Bayesian reasoning in action with a medical diagnosis example. Imagine two hypotheses: a patient has cancer or does not. We know the disease is rare and the lab test isn't perfect. By applying Bayes' theorem, we can calculate the probability that a patient has cancer given a positive test result. This approach helps doctors make better decisions by considering both prior knowledge and test accuracy, rather than relying solely on the test outcome. Practical scenarios, we summarize the situation using key probabilities: the prior probability of disease, the accuracy of the test, and the observed result. By normalizing these values, we can determine the exact likelihood of each hypothesis. This method ensures that our decisions are grounded in both data and statistical reasoning, reducing the risk of misdiagnosis or overconfidence in uncertain results. Bayes' theorem isn't just for medical tests, it's also central to concept learning in machine learning. By calculating the posterior probability for each hypothesis, we can identify the most likely concept that explains our training data. This brute force approach, while sometimes computationally intensive, provides a clear and principled way to select the best hypothesis from a set of candidates. Consistent learner is one that makes no errors on the training data. Under certain assumptions, such as uniform prior probabilities and noise-free data, every consistent learner outputs a map hypothesis. This means that algorithms like FindS, which always find a hypothesis consistent with the data, are essentially performing Bayesian inference under the hood, even if they don't explicitly use probabilities. Learning continuous valued functions, such as in neural networks or regression, the maximum likelihood hypothesis is the one that minimizes the squared error between predictions and actual values. This approach assumes that noise in the data follows a normal distribution, which is a reasonable assumption in many real-world scenarios. By minimizing squared error, we're effectively maximizing the likelihood of the observed data under our model. Naive Bayes classifier is a simple yet powerful tool for classification tasks. It assumes that all attributes are conditionally independent given the target value, which greatly simplifies probability calculations. By multiplying the probabilities of each attribute value, we can efficiently determine the most likely classification for new instances. Despite its simplicity, naive Bayes performs remarkably well in many practical applications. Let's apply the naive Bayes classifier to a classic example, predicting whether someone will play tennis based on weather conditions. By analyzing the training data and calculating the relevant probabilities, we can classify a new day as likely or unlikely for playing tennis. This example illustrates how naive Bayes uses observed frequencies and conditional probabilities to make accurate predictions, even with limited data. Bayesian belief networks extend the power of Bayesian reasoning by modeling complex relationships among variables. Represented as directed acyclic graphs, these networks capture conditional independence assumptions and allow for efficient computation of joint probabilities. Each node represents a variable, and the arcs encode dependencies, making Bayesian networks a powerful tool for reasoning under uncertainty. Learning Bayesian networks involves estimating both the structure and the conditional probability tables from data. When the structure is known and all variables are observable, learning is straightforward. However, when some variables are hidden or the structure is unknown, more advanced algorithms like gradient descent or the M algorithm are used. These methods allow us to optimize the network parameters and make accurate inferences, even in complex, uncertain environments. Expectation maximization algorithm is a powerful tool for learning in situations where some variables are hidden or unobserved. For example, when data is generated by a mixture of several normal distributions, but we don't know which distribution produced each data point, the algorithm helps estimate the underlying parameters. By iteratively updating our estimates, enables us to find the most likely explanation for the observed data, even in the presence of uncertainty.